we went from gravitational waves to biological waves. So I mean, we only changed maybe 20 orders of magnitude, but okay, it's fine. Okay, all right. So I'd like to tell you about some very recent work on biological tissues, and I'm going to tell you in what sense is extreme mechanics, what we mean by that. But first, let me just say that this work done in collaboration with a number of people. Particularly, I would like to point out Si-Han Chen, who is actually in the audience. He's a postdoc, and Efe also contributed a lot. Michel Fouchard, that you heard in this collaboration before, and then the experimental part of the team, which is Victor, Pascal, and Miriam. And the first thing I think I owe you is an explanation of why do we even talk about biological tissues in this context. I mean, this is a crowd where it's more common to hear talks about metamaterials, et cetera, including me, frankly. And so I would like to argue that this is really an example of a chiral non-emission metamaterial, except that it's not a metamaterial, it's a biological tissue. And in fact, and this is not just a metaphor, you know, roughly at the same time that we were working on this project with Andrea and other people, we were writing this review that I don't remember how we called it, Andrea, maybe symmetry-driven mechanical or phononic metamaterials. And of course, more than symmetry-driven is symmetry breaking. All the symmetries you can break. Primary one is, of course, hermeticity. Some of the people who have worked in the audience on these things are here. And so this is an experiment. The experiment is the following. In my opinion, our field of metamaterial has reached a degree of maturity that some of these ideas, you could imagine deploying it to try to capture observation in natural phenomena. Now, I would like to convince you that biological tissues of multicellular medium present all the crucial feature necessary to do this analysis in detail, and I want to show you how to extract those things from data. So let me get started. So chirality, okay? So the question I'm particularly interested, and actually I should go back about this. What you're going to hear in this talk is things like tissues that are chiral in some sense, and they display microscopic flows along edges, okay? They break parity explicitly, okay? And what we're particularly interested is the phenomenon of chirality transfer across scales. Simply put, what happens inside the cell that prompts this macroscopic flow? And how do you connect what happens inside the cell all the way to a macroscopic response, entirely out of equilibrium? What we want to do, in a sense, is equivalent, not equivalent, is a out of equilibrium version of an exercise that was probably pioneered for the first time by Louis Pasteur. So Pasteur is one of the first people who was able to trace the property of chiral structures, crystals in particular, all the way down to the breaking of chirality at the level of molecules. The legend says that he discovered actually this while scratching barrels of wine and tartaric acid, which sounds a bit apocryphal, perhaps a slightly cheap characterization of the interest of most of my French friends. But this is what is being narrated. And of course, the exercise of Pasteur has been replicated many, many times. And one peculiarity about this is that you're connecting a microstructure to a macrostructure. Everything here is equilibrium. And of course, this has been done many, many times ever since. What we want to do here is some form of characterization of active processes inside the cell that can be connected quantitatively to measurable macroscopic flow experiments. So here, both what happens inside the cell and what happens at the macroscopic level are non-equilibrium responses. And we want to connect them in the sense of an explicit coarse graining exercise. Okay? This is the goal. And in a way that matches experiments. So I want to give you an idea of how the experiments look like. And this is the first sobering experience, at least was for me, as somebody doing physics, even metamaterial, which typically present data that are pretty clean, certainly by the standard of soft matter physics, when you try to approach biology. So what you see here, instead of this very beautiful, idealized flow at the edge, I'm going to show you how the data look like. So first of all, you're seeing here a tissue in a channel geometry. So the tissue is quasi-two-dimensional, is on a substrate. So there is a notion of a bottom and a top for the cells that would be essential to define chirality. And what is being labeled here for a bunch of cells is the position of the nucleus of the cell. And I'm going to play a movie. There's going to be an awful lot of noise. But please pay attention to the fact that the flow in the, if you like, bottom in terms of the screen and top edge of the channel are going in the opposite direction. So this is what I first saw from Pascal and Victor when a year and a half ago in the Curie Institute. I was first exposed to this movie. I'm going to play it for you. Can you see that on the top, the flow is going like this, and in the bottom, it's going the other way? And of course, I mean, we can collect statistics, and I'm going to show you the data with statistics. But the first time I saw this, the two things were, my first question was, is this always like that? You know, there is a notion of top and bottom because it's on a substrate. So this question is meaningful. Does it always break parity in this way, or is it half of the time one way or the other? In more explicit language, is this an explicit breaking of parity, or is it a spontaneous one? And what I was told, no, it always goes like this. Okay? So the chirality.
15 up there, so that was a 5-hour movie?
Yeah, it's very slow. And the second thing, which I don't know if you reacted like that, I looked at this and I say, how can you do theory on this? Yes. I mean, like with this type of data, it's intimidating, and you know, it's reasonable. You know, this is not a mesoscopic experiment. Let's put it that way. But I want to do parameter-free fitting of currents with the same degree of pedantic attention that you would do in a mesoscopic experiment. Doug, hold me accountable. Okay? I picked up, I think, a good guy to hold accountable. Because so first of all, a spherical cow model of a cell before we go into data-driven inference from data. One very simple way to think of a cell is being composed by fibers that are illustrated inside here. This is the cell membrane. Inside the cell, you find these fibers. These fibers are usually under contractile forces exercised by molecular motors. So to zero order, think of these fibers as springs that are being held under compression. Okay? And as a result, there will be a typical inward force that I'm characterizing with the symbol F parallel. Okay? There's nothing chiral about this cell. However, there are some classes of cells for which, if I actually look at the arrangement of these fibers represented here by this pattern, you can clearly see a net chirality. And most crucially, you can see an angle that these fibers are tilted. If you allow me to sort of draw it by hand, not that these two things are identical. Of course, this is an isolated cell. When you put them in a tissue, they also deform. But please notice that the difference between here and here is that here I've assumed that all the inside the cell, the organization of these fibers has an inherent chirality controlled microscopically by some protein. And there is evidence for many cell lines about this. Please notice another big difference with the metamaterial world. In metamaterials, we build. We know the microscopic rules. Often we want to do inverse problems. But here, in the case of the cell lines that Pascal showed me, we didn't even know microscopy data like this to corroborate. So we are trying to infer what's happening inside. But we do know that chiral cells exist, and that's how they look inside. Okay? So how do we mathematize this simple situation? Please notice that if this fiber is under tension, held still by those molecular motors, since it's at an angle now here, and we assume that this angle is always one sign, not one magnitude, but always one sign, there's going to be also a projection along the perimeter or the membrane of the cell. And in particular, if this angle is on average theta, then there's a very simple relationship between this transverse force and the longitudinal one. If you call alpha 0 a chirality parameter that is the tangent of the angle theta here, then F perpendicular and F parallel are simply related by this. Is this clear? Now, this, while very, very simple, is rich in consequences. And please notice one thing. If I take these transverse forces and I do a circulation, a line integral, along this cell, is non-zero. That means that that force cannot be written as the gradient of a potential. Okay? That means that if this cell is in isolation, it will rotate. And even if it's not in isolation, and there are other cells that hold it stuck, there's going to be intracellular forces that are non-conservative. Okay? So the macroscopic response of this medium is not going to be your elasticity that you derive from a gradient. And this will have consequences for the non-hermeticity of the dynamics describing this. I'm going to get there momentarily. Okay? Now, this is a single cell. Of course, what we have is something more like this. If you like, the term that people often use is a vertex model. So many polygons that are the cells sharing membranes, cell membranes between them. And so if this is the cell center, okay, you can draw a vertex model by a Voronoi triangulation. Is a construction that allows to obtain that. And then the question is, what is the dynamics that describes the evolution in time of that discrete structure? You see, what we're doing on this slide called vertex model, we are defining a microscopic model. This is the equivalent of what you would do if you write masses connected by springs if you wanted to derive elasticity by homogenization. Okay? But and people have done this game. They've done it for tissues, they've done it for foams. And one common choice is to assume, in order to model these forces that are pushing outwards, the conservative one I call F parallel, you just write down an energy that penalizes deformation in the perimeter and in the area of each of these polygons. That's an energy. And then you take a derivative of the energy with respect to the position of the cell, and that's the dynamics. Please notice that this is a variational dynamics. Okay? A dynamics that assumes that you go down energy in the energy landscape. Please notice that it's impossible to describe like that forces that are non-conservative, that are non-curl-free. Okay? So this is not going to be enough for us. So we have to take this standard model that describes, in a very simplistic manner, tissues, and add something. We need a non-variational vertex model. Okay? How do we do that? Well, the answer is, of course, this is different, okay, from the gradient. And I'm just going to give you the answer. The force that we want to capture is this here. F tangential can be written as the gradient of a potential. And then the only thing that you have to do, you multiply by EZ and alpha naught. And the only thing that you see here that looks like this Jacobian here is that you can define the problem either in terms of the center of the cell or the center of the vertices. And this Jacobian here is accounting for that. So all I'm trying to say is that this is what normally people use. We just have to add in red a piece that cannot be written as a gradient of an energy. And now we have a microscopic model that incorporates that simple statement about a parameterize via this parameter alpha naught, the chirality, and the non-conservativeness of energy of that model. Okay?
Did you tell us what the C is?
Yeah, I didn't tell you, but I can tell you now. So if you write down this energy as this two quadratic form. One piece of that, when you expand it, one piece, this perimeter squared, is EC, and that's where this comes from. Okay, I skipped it, but it's all under control. Now, when you look at this, again, this is a conjecture, right? Who knows if that complicated system is actually described by this? I would, if you ask me, I would say this is nonsense, right? And that was pretty much my reaction when Sihan somewhat, with a lot of intuition, proposed it. What was the reason for my perplexity? This is a generator of macroscopic trajectories. It's function of 1, 2, 3, 4 parameters, to which we are now adding another one off a naught. What are those parameters? What are the ways that we know of testing and falsifying this proposal as a generator of the dynamics? In order to do that, we would have to take many noisy movies, like the one I showed, and fit on this very high-dimensional data this model. Okay? This is not an easy task where there is a lot of noise, and it's a task that is very common in computer science and at the interface of modern machine learning method and inference. This brings us the second big item in today's talk. When you build something, you know what you put in. When you try to describe what God presumably has built, you have to do initially an inference study of the model itself and the validity of the model and the parameters. If you want to construct the model with microscopic knowledge of the data. So how do we get this microscopic parameter? How can we solve this problem of fitting this model on high-dimensional noisy data? And the answer is nada. And this is not speaking Spanish. It's an acronym, Nudged Automatic Differentiation Algorithm. And this algorithm, it's predicated on my Catholic belief that I was brought up thinking that from every sin there is a virtue. The mathematical equivalent of that is that for every singularity there is a regularization. Neither of them are true, especially the first. But I'm going to show you that this is one of the cases. I'm going to tell you what it is. First of all, let me tell you what we're going to do. The observable is the velocity field defined cell by cell for how these cells are moving. And it's a function of their position, parametrized according to that model by all those microscopic parameters that we want to extract from the movies. So in principle, you could say, well, look, define a loss function. That's to say a quantity that you define by make an assignment to start with these parameters that you're going to iterate, evidently. Generate, using the model, the prediction for what the velocity field, not the velocity field, the velocity trajectory of each cell is, subtract it to the experimental one, and try to minimize this quantity. Okay? This can be done in various ways with different degrees of intelligence, but one thing that is kind of common in all of this minimization is that you're going to take a derivative of the loss with respect to the parameters. Okay? That would be a gradient descent algorithm of any sort. Now, and of course, it doesn't have to be an explicit function. It could be a program itself. And that's what the basic idea of automatic differentiation is. But the point is, this works particularly well, or it works at all, when the data is differentiable. If by any, atrocity, your data, even with a little bit of noise, loses the differentiability, then this is a real problem. This is what I call the singularity of the perturbation of the noise. And that is what requires a regularization. So let me show you explicitly what it is. What we did is we generated data on a computer with that equation. And then we said, can we actually learn the model that we generated, where we know the parameters, we know the ground truth, using this technique that seems very reasonable? We try. So this is the actual position of the cells in the model. The model is deterministic. We put a little bit of noise, tiny amount, So the center of the cells get displaced a little bit. The difference, even on synthetic data, between the numerical experiment and the prediction of that model on the velocity field has this degree of inaccuracy. You see what we've done? We ran this, we found the optimal number of parameters, and even on synthetic data with noise added by hand, this is how poorly we're doing. Okay? And the reason is, there is a singularity. What is the singularity? Is what is technically known as T1 events, both in mathematical study of forms and in tissues. Please notice, if I take these centers, the black one, say the one without noise, and I triangulate, I Voronoi tessellate the plane, I get the black network. If I do it with slightly off by noise data in pink, I get the pink one. And the two have undergone a topological change in the network. When if that happens, well, there's all reason to believe that something that assumes differentiability may not be the way to do this. So the solution that Effe came up with is to nudge the data. Or, if you like, to don't fit the model to the data, fit the data to the model. This really looks like scam. But what we're doing is the following. We're going to assume that we are going to push the data a little bit by tiny amount in the direction that undoes the perturbation due to the noise. You say, well, how do you know what the direction is? Well, it's the direction that minimizes the loss. And in order not to have too large of a push or a nudge, we attach a spring to the center of the position of the cells. Okay, so to find a way of not nudging too much. So the algorithm is named after my cat, Anubis. But if you have a cat, this happens all the time. If you have a cat, an object that is very close to an edge, like your table, the cat is going to go there, is going to piss you off by pushing it all the way down. And this is exactly what this algorithm does. And the table is a landscape of the loss. So slight nudging takes you all the way down to the minimum because it's essentially extremely sensitive to the noise. Okay? Now, you can judge the quality of my explanation. It's probably not great in 2 minutes. I mean, you can also read how we did in detail. But the result on synthetic data is to go from this to that. Okay? So in other words, when you run the same automatic differentiation algorithm with the nudging step, the parameters that you find as an optimization gives you this disagreement between. This is on synthetic data. Now that we know that it works on synthetic data, we can go back to the real data that we have. And of course, we can do it for each single cell. And what you have here is the inferred flow field. This is Vx and this is Vy. And these are color code. And of course, you can do it quantitatively by taking differences. And even with the real data, it works remarkably well. So what have we done now here? Just to step back to the big picture. We proposed a microscopic model, and we gave you an algorithm that does two things. One, it tells you how well you're fitting the data, because you can just look at the loss and see how close you are. In this case, we are very close as you can ever get. Second, it gives you the value of all these microscopic parameters. Okay? Now we know that if this was a simple solid made by masses and springs, we know the value of the masses and the value of the springs. So in principle, if we are able to coarse grain, we should be able to obtain an hydrodynamic theory without free parameters, if you can really do the coarse graining. You should be able to say, what is the bulk modulus or the shear modulus of that medium as a function of this quantity that you obtained. Okay? And that's the thing that we did. Next thing, towards a coarse grain theory. You see the logic, micro, coarse grain theory, and then we're going to predict the experiment. And if we can pull it off, we're going to predict the experiment with no fitting parameters and just predict the flow. So this is the equation of motion. This is the displacement field. This is over damped dynamics. These are the equation of a simple solid. You have a shear modulus, shear viscosity, viscoelastic model, bulk modulus, bulk viscosity. Okay? And you could imagine somebody can tell you the shear modulus, by coarse graining it, by homogenizing, we can tell you how the shear modulus depends on all those microscopic parameters. Okay? That's what we did. But please notice that already you know that the answer cannot be only this. Okay? Why? Those are the equation of motion, at least for the specialist, of a normal viscoelastic solid. By normal, I mean passive, essentially. Okay? The question that is really interesting is, how does at the hydrodynamic level the presence of those forces that are non-curl free, non-conservative shows up? Okay? If you want to represent the constitutive relation of the material, stress versus strain, the shear modulus is a diagonal component in the stiffness tensor. One thing that you might have heard me talking about is that purely on consideration of symmetry alone, this matrix need not to be symmetric, the stiffness tensor, if the material does not conserve energy. Okay? You can have something known as odd viscoelasticity or odd elasticity. For example, you could have here a K0 and a minus K0. This term here, if you do a circulation in strain space, brings energy in or leaks energy out. Okay? It's connected with activity. Now, in this theory, you have terms like that because they are allowed by symmetry, and we can calculate what they are as a function of the microscopic parameter. Notice one little thing. There's a lot of equations, but none of the parameters entering here, the passive moduli, are related with the alpha naught. Because when the alpha naught goes to 0, this goes to 0, but not the normal shear. You see what I've done? This is like doing the exercise of deriving the shear modulus of a solid as a function of the spring constant, but with those weird additional pieces. And not only it modifies a little bit the normal moduli, it generates a new one. I can predict the existence of the new one purely based on symmetry considerations, and we've done it in the past. But what I want now, and that's why I need a micro theory, is to get the numbers, get the prefactors, the coefficient in front. Okay? And this is what I have now, because I did the coarse graining explicitly and the inference exercise. Is this clear? I've been a bit quick on the form of this equation, but please notice that here I just show you the shear part, but elasticity in 2 dimensions is a tensorial theory that requires at least 4 things. There's also dilation and rotations. And similarly, in addition to the bulk modulus that relates dilation to pressure, there can be now this weird term A that relates dilation to torque. Okay? This can only exist if you, again, like this K0, if you assume that the stress is not the derivative of the energy of the medium. And hence, this tensor need not to be symmetric anymore. This is the connection with the non-Hermitian and non-reciprocal stuff. Okay? And of course, if you study this equation, you're going to find traveling waves, exceptional point, whatever you want. Okay? And of course, since many of the people who invented this stuff are in the audience, I'm not even going to go there. My question today is, to what extent these ideas can be applied to messy data of the form that I'm showing you? Because I think that that's a really tough test, much more than if I build it in my lab.
It's all linear, though, right?
This is all linear too. This is all linear too, absolutely. There could be also nonlinearity. Now, there's a bit of parsimony, because the more parameters I put, however, this is a good point, because since I have the microscopic model, now the parameters are no free. So if I want to go do the derivation on steroid, I can derive also the nonlinear term, the nonlinear coefficient as a function of those microscopic things. Not a walk in the park. But let's.
That also has some hope since it's linear.
Well, you don't know, because you don't know in what regime the experiment is. I think it's a fair comment to say, what about the nonlinearity? What we're going to do is that we're going to assume this model and see whether this is enough in non-fitting, in matching the data. Okay? Now, up to now, I would describe this really as an active or non-Hermitian chiral metamaterial. But it is biology after all. And there is one thing that is crucial. Please notice that when I was describing, I never bothered to write down an equation for the density or the masses. Nobody would think that these masses disappear out of nowhere. But remember, what we have here are cells. And guess what? Cells are born and they die. So you need to write a continuity equation that has sources and sinks, reflecting the creation and death of the cells. This is the additional equation you have to put. This is a continuity equation for the density of the cell. And there is one for proliferation and one for extrusion or death. The thing that is interesting is that in tissues, these quantities are not homogeneous in space. And in particular, our experimental friends can measure these quantities. In other words, they can say how the cells tend to proliferate more the more you go towards the edge. Okay? Now, intuitively, I didn't know this, but when I told my buddies in the lab at the Curie, they told me, well, even somebody like you might have realized that if you take a knife and you cut yourself, right, there's going to be blood coming out, and then it's going to close. Right? So those are the cells that at the edge, if you want to call it that way, when you made the cut, are clearly proliferating more to close. Okay. Now, by how much and how you quantify it, this is something that the experimentalists did. But now I want to draw your attention to the fact that we have a closed system of equations. If the experimentalists give us this function and that function that they did, and I'm going to show you on the next slide, we have this completely fixed without no free parameters. We can solve them in a channel geometry, as if this was an experiment in your favorite theory of transport that you want, okay? And compare with the data. And besides the precision measurement comparison, we can also try to attempt a delineation of the mechanism that leads to the edge current, even qualitatively. And it's the following. It's something that we called self-pinching. Take this picture in mind. Let's start here. What you can see here is the density of the cells. This is data. This is experimental data. This is the width of the channel, okay, that you see here. And this is the measurement of the density. This is the proliferation rate. The fact that the cells are proliferating at the edge means that there's going to be a surplus of compression right there. You see? What I'm trying to do is the following. When you're a material guy like me, you think of rheology in the following terms. There is a material sits right there. I go there and I do a perturbation. I see how the material responds. The multicellular system here regulates itself, decides to create more cell in some parts, and by doing so, it pushes on itself in selected places. In particular here, it's pinching at the edge because the density of the cell is higher there. So if this was a normal material, I pinch like that, the response is going to be purely forces longitudinally. But in this material, where coupling exists between dilation and torques via those strange moduli, there can be a transverse response. You see what I'm saying? This transverse response is the macroscopic equivalent of those transverse forces at the micro level that depend on the longitudinal one. And in a way, the ratio of these two is something that we can really track all the way down to the microscopic parameters, okay? And make a prediction. So what the experimentalists did is that they generated many profiles of flow and extracted the relation between Vy, the transverse flow, and Vx as a function for many samples of different width. This is their data. There's a little bit of scatter, undoubtedly. This line here is not a fit. It's this formula with the alpha naught, the P naught, and the L naught extracted from the microscopic theory. And this A is just square root of 3 over 2. That's it. Okay? And of course, we can fit also each profile if you want individually. So to me, this is really a smoking gun of the existence of this exotic, or I mean, for people in this audience, maybe not so much, extreme wave and mechanical responses, non-Hermitian primarily, that we've been discussing in this audience, and some of you have predicted decades ago, maybe not in elasticity, but you see the structure mathematically that emerges. Now, a second thing that happens is that since the elasticity is slaved to the proliferation of the cells, this proliferation of the cells changes in time. Typically, the cells can increase the number or decrease it, depending on how that happens, they will move in the phase diagram. And so what we have done is we've taken these microscopic parameters and the cortical chirality parameter and drawn a phase diagram that separates the different phases. Now, if this alpha naught was 0, if this was a purely conservative model, which is what has been studied up to now, you would just leave on this line, okay? And you would have a transition, essentially, on this line from a solid for low value of the perimeter to a fluid. This has been studied extensively, okay? But once you open up, once you include this chirality parameter, you no longer have only static phases. You can have time-dependent phases. Now, all of you have studied exceptional points. Once you hit an exceptional point that you can have here, because all these matrices are non-symmetric, you'll have traveling states. Similarly, here you're going to have solids that display at steady state some sort of chiral motion, as if they were a particle in a magnetic field, okay? But it's due to the forces. And so we can write this phase diagram, and since we know what are the microscopic parameters, we can take a cell line and parameterize the behavior as those cells evolve in time and how they move inside this phase diagram, and extract the corresponding moduli as a function of time. You see what I'm saying? The moduli in this medium change as a function of time because the forces are generated by the degree of compression, and the degree of compression is function of the density, and the cells keep adapting their density by living and dying in a spatially dependent manner also. Okay, it's an adaptive material.
But why isn't it on average stationary?
Because life is not a steady state, it's a transient, right? I mean, this is not even a joke. Like the assumption that the thing go to a steady state, in biology, that's called death. I really don't know how to say it differently. And now, when we see this, we said, okay, what can you do with a material that has a non-reciprocal response function, moduli, that depends on time? One of the things that you can do is to consider this, now let's call it a biological metamaterial, as a platform that you can train to learn dynamic functionalities. So I'm going to have a bit of a jump here, and I want to bring you to a completely different world from the one that perhaps we've been discussing up to now, which is since the time of Hopfield, there's been a very strong interest on physical learning, or systems that are not necessarily comprised of neurons, that can learn a pattern, for example, okay? And that can be done, it's a very strong topic now. What I want to ask is that how do you get a material to learn a sequence of patterns? How do you get a material to learn a pathway, right? Not just to assemble an origami, but to make an origami bird, but to make that bird also, how do you say, flap its wings, okay? And the answer is what you need is non-reciprocity. And I want to show you to you now by showing you the connection between this matrix here, the stiffness tensor. It's a matrix that tells you how the fields are coupled. In spin language, you would call it an exchange interaction, the Jij for the spin. So what I want to show you here is a way of implementing some of the lessons that we learned in the biological metamaterial in a toy. So let's go back to the metamaterial now. So this one is not even a metamaterial. This is my favorite experimental platform, Lego robotics, okay? So Lego robotics is Lego plus motors and sensors. Cost maybe less than $100 for 5 or 6 of this. So what I'm going to show you here, if you like, is a non-reciprocal spin model. That's a bit of a mouthful. There are 2 spins. This is one spin. This is the other spin, okay? And each of them is parameterized by an angle, θ1 and θ2, okay? And if this was a normal spin model, well, they just want to stay aligned to each other. But now I'm going to consider the possibility that the way the spin 2 interacts with spin 1 is not equal to the way the spin 1 interacts with spin 2. This matrix Jij need not to be symmetric. Very much like our elastic moduli is not symmetric. And second, I want it to be time dependent. So here, since it's a metamaterial, I don't have to learn what the cells are doing. I'm just going to make it. I plan it in Arduino, whatever it is that you like. So here I have an equation of motion for J. So this is the equation of motion for a spin system. This cosine, this sign here is the derivative of a cosine. Okay? But notice that since we're not assuming that comes from an energy, Jij can be asymmetric. And in fact, it's not just asymmetric, it has its own equation of motion. Okay, can you see this? So now, if I want to train my material, I'm going to move by hand these angles so that this equation will generate a new J. Okay, can you? Now, look at this equation. This equation has a kernel. This is a cosine, and this maybe is an exponential. Notice that here, if I flip I with J, I flip T with T prime. But if this is an exponential, it's not going to give me something symmetric. Okay? So what I'm assuming is that when spin 1 talks with spin 2, there's a delay. Okay? And this delay breaks the symmetry of the training rule, Hebbian, that is, fire together, wired together. Because now there's a delay, so you can break that symmetry. Okay? And in neuroscience, this is called spike timing-dependent plasticity. So now I want to show you what happens. I'm going to ask the question, under what condition, if you have a system of equations like this, where there are exchange interactions that are time-dependent, potentially leading to non-reciprocity, under what conditions can you learn a dynamical state? And I'm going to show you the most stupid of all. But in your mind, please don't think only of this. Think about maybe in optics. You guys know how to make non-reciprocal, non-emission response. You can imagine something more sophisticated than that. Here it's just a principle. Okay? So first stage is what I call training. So I'm going to move this angle back and forth. And as a result of this dynamics, the J will change. But during this training, I'm going to first do the case in which I move them in a sort of reversible manner. Okay, I don't break time reversal symmetry during training, which means that I'm going to learn a symmetric interaction. Then I switch off a button that no longer makes that dynamics active. And this is a button because I built it, unlike the cells. And now, if I just play with this, the only thing that it's going to do is to learn how to align. Okay? Why? Because it can only learn the fixed points. And the fixed point cannot correspond to something dynamical. So that means that even if my system has the potentiality of generating non-reciprocity, if you train it with something that is time reversal protocol, it will never learn it. Okay? Now you can say, well, okay, then I'm going to go back and I'm going to train it with something that does break time reversal symmetry. I'm going to just make it rotate all with one way. Do you see what I'm doing? Now, same equation will generate a Jij that is not necessarily symmetric, very much like the K0 that we're varying as a function of time in the cells, except that there is wired by God knows what complicated mechanisms. Now, if I switch off the training and I go to the dynamics, you see that if I touch them, they've learned the limit cycle. Okay? You can do an exercise which is the quintessential example of futility, a toy model of the toy. Right? The advantage of this toy model is that you can solve it exactly, amusing yourself with response functions. And you can extract the two conditions that are crucial. One is the non-reciprocal interaction must be allowed, and they're allowed by this time delay, which is going to have in any physical interaction mediated by causality. And the other condition is that during the training, you have to show time reversal symmetry breaking examples. Otherwise, it will never learn this. So if you like, there is a condition on the hardware, and there is a condition on the training. Okay? And the last thing that I want to show you is an example where you can do this with particles. Okay? And this probably is the closest that it's going to get to potential realization, for example, in optical metamaterials, because we're going to turn this, in the spirit of one of the talk earlier on, into a discussion of what property of Green's function, a retarded Green function that depend on that delay, will support this. So what type of particles can learn to assemble these dynamical patterns? Well, they must have non-reciprocal interactions. And so, I mean, the way I like to think about physics in general is almost like a game where there are two actors, the particles and the field. Okay, often they're dual to each other. In this game that I'm going to play today, you really have to play simultaneously with the motion of the particle and the field that they generate. Let me tell you how. Here is one example. Imagine that you have particles, and what I'm describing as an experiment done very recently in this article that I'm going to present first to you in a more empirical way. Imagine that you have an oil droplet. Okay? So an oil droplet is not a neuron, right? So we have a bunch of them, and we want to teach them some adaptive dynamical functionalities. So this droplet of oil moves, and as it moves, it lets out oil. Okay? So we have the position of the particle labeled by R. I is the index of the particle. And then there is the concentration of the oil that it emits. This is the field. And if you don't like oil, you can think of some other field that is being emitted. But the point is that these particles move self-propelled, okay? And as they move, the oil that they emit is no longer a circle. It's like a corona. This always happens. Maybe even Cherenkov radiation is a bit like that in other contexts. And so the degree, if there is a corona now of this oil, and if the two particles are going to interact via this field between them, then since it's a corona, you know what is corona even an English word? An asymmetric object, right? There's going to be a difference between the guy in front and the guy behind. Do you see what I'm saying? Because you get it if you're here, but you don't get it if you're there. So if they talk via that field, you can now build a field-mediated interaction that breaks reciprocity. Okay? But the crucial thing is that and these things in physical chemistry are called Marangoni forces. Okay? Now, these Marangoni forces tells you that the way a particle I will move depends on gradients of the oil emitted by another particle J via a coefficient omega ij that tells you the weight of this effect. Now, this mobility omega ij, or cross-mobility omega ij, is now playing the role of the jij in the previous experiment. And what we're going to use is a learning rule inspired by the experiment, in which this affinity varies because once a particle emits the oil goes on the other particle, and that changes the omega as well. So if you do a plausible mechanism for that, you get now an equation for omega. Okay? This is an horrible mess, but it's a mess that can be used to model reality. I won't go into detail. And what you can do in particular here, so that we take away a bit of the context, you take this equation here, and you solve it with a Green's function. This Green's function will have retardation effects because of those delay. And so you substitute here an expression for how the omega ij are evolving with this Green's function. And the conclusion is this. Time asymmetric delay in the learning rule, which is what we need to learn time-dependent phases, emerge always from any causal interaction. You see what I'm saying? No matter what was your field, clearly light is particularly bad because it propagates really fast. But as long as the field is not propagating at a speed that dwarfs the propagation of the particle, this may not be easy to do in optics, for example, then there will be an interplay between the two. And you will change this omega ij in a time-dependent function. If you can do that, if you work at, one thing that you could say is that, look, when you add your LIGO, your metamaterial, you have a button. You switch off the button, and you can switch the training. But how do you switch this equation in a natural phenomena? Well, there is something called Peclet number. Okay? Peclet number is a ratio between velocity, diffusion coefficient, and the size of the particle. Depending on this number, loosely speaking, during the training, I'm going to move the particle, say with a tweezer. If I move them fast, this equation is dynamically present. If I move them slow, a low Peclet number, this equation is irrelevant, so I'm not training. So if I switch between fast motion, a high Peclet number, to slow motion, I can go from training to retrieval phase. And I'm going to show you, last thing, a picture. So here, what we've done is we've shown this particle during training a circular motion, like this. So imagine that we go in the lab, we move them, okay, like this. We teach them to go in a circle, like a merry-go-round. And we do that by moving them fast, in the sense that this quantity must be much greater than 1. Okay? That's our training stage. Then we stop. And one thing I should have showed you is that while this moves, the omega ij are changing. And notice that here I'm going to plot omega ij and omega ji. And as this move, notice that the omega ij go to, omega ij and omega ji are not equal to each other. Can you see that? Okay. So at the end of the training, I have an asymmetric omega. Then now I go to the, retrieval phase. Retrieval phase, I'm going to let the particle move as they want. I don't move them. And they're going to move at speeds that are much smaller than the one I was moving. So now the Peclet number is much less than 1. Means that the equation for the omega is no longer at play. I only have this 3-1. And I want to see, if I let this particle go, will they actually show the dynamics that they allegedly learned before? And this is what you see. They first assemble, and then they go. Now, of course, I don't know if the world needs this rotating motion, but you can see that these are the minimal building blocks built from the symmetry and the breaking that are arising from it. And you can do other fun things. You can do, during the training, teach a bunch of particles, like a spaceship, to chase the other one. And then in the retrieval, the spaceship is not even assembled. It assembles itself, chases the other one, and catches it. This is a functionality where you literally taught a bunch of particles to be a predator and another one to be a prey. Okay? And it's freely inspired by video games at the time when I was a kid. And you can imagine there could be things that are more complicated. So with that, let me conclude and say, I started with a real-world example where I show how in biological systems you can have these non-Hermitian responses. I show you that these odd elastic moduli were time-dependent. And by going to simple examples where instead of having interaction between different strains at a complicated tensorial structure, you just have a Jij, but still the asymmetry, I showed you how that condition of the time evolvability of the moduli is what you would need in a real material to replicate the learning of dynamical phases that is required for a dynamical version of the upfield model. With that, let me thank you for your attention.